Everyone, so what we learned with straightness tolerance and what we've seen again with flatness tolerance is that your size tolerance does have a built-in form tolerance. Like you can't have a form that breaks that perfect form boundary if you don't have a straightness tolerance or something else tolerance applied. Now, this is not the case, however, for a skewed or inclined surface because they don't have a size tolerance. Like this surface right here, there's no size tolerance to give you a built-in form tolerance. There's no perfect form boundary to restrict it. So if you want to constrain the flatness on that surface, you're going to have to specify a tolerance. And you can either do that with an extension line, which I think looks kind of wonky, I'll be honest with you, or you can do it with a leader line, which I prefer. Now that's just my preference. I will not count you wrong if you do that. But look at that. Seriously, that kind of angle right there, that bothers me. That bothers me. So you're going to have to control it in that way. Now, what will it look like? Well, in the end, you will have a tolerance zone that's 0.005 inches apart, which is the tolerance you gave it. And then you will have somebody test this by reorienting it constantly back and forth until they minimize that full indicator movement, which is that little gauge. You zero it on the surface based on your current configuration, and it moves back and forth from the surface. And you reorient it because the full indicator movement, this gauge doesn't change its orientation. You change the orientation of the part. So, like I said before, there's actually multiple ways to measure surface flatness. Most common is you have your gauge, your indicator, which is perfectly perpendicular to the surface that you're measuring from. Okay, it's perfectly perpendicular to that. And you will move your piece back and forth on it over and over again to see what the full indicator movement is. The issue is that you're trying to get this top surface as parallel to your table as you can, but you're not necessarily correct. Like you might be off. And if you are, you're going to have to keep on checking it to make sure that you're really correct, that it's not flat. Because if it's oriented like this, your indicator is going to say, well, this one's really, really high and this one's really, really low. It doesn't say like, oh, well, I need to be perpendicular to that when I turn. No, it stays the same. Your part has to change. Now, there are some cases, though, where you can have a really easy time of it. And that's when you have a small piece and you actually have the indicator that's built into the table. So by necessity, if your surface that you're measuring the flatness of is against the table, well, then they're already perfectly parallel. It's already perfectly oriented, and then you'll be able to check it very, very quickly. But this works only with fairly small parts. Now, luckily for us, we don't have to do this by hand. This can be automated. We have computers to help us. It's just, honestly, form tolerances are probably the hardest ones to measure simply because there's no control on how you are constraining it or how you're holding it when you measure this. Okay, one last thing for flatness is that there can be a unit area flatness. Just like there was a unit length, we can have a unit area flatness. And just like with straightness, this is going to change how quickly the flatness can change. So you'll have an overall larger flatness tolerance for the entire surface, this entire continuous feature. Not for this section. That section doesn't get controlled. And then you'll have underneath that a smaller tolerance that has this per symbol. And then you'll have dimensions of what your area is going to be. In this case, it's square, because it gives us the square symbol, and it's 1 inch square. So you're going to check each 1 inch square and make sure it doesn't change by more than 0.003 inches in that 1 inch square. However, if I go over like 10 inches, I can go up each time by 0.003 inches, as long as I don't keep on break that 0.01 inch boundary. It's just each of these individual squares I am checking cannot change by more than 0.03 at a time. So these unit area flatness, unit lengths, straightness, it's constraining how quickly something changes. Remember that, okay? That's the important detail. So that's it for this time. Thank you very much for listening, and I'll see you all later. Bye-bye.